So now we're looking at wave functions. We're looking at quantum mechanics, and we're going to see these wave functions, how they describe different particles. Now, it's very, very important here to try to get um, the basic principles here. Try to look at this on more of a conceptual level because the mathematics can be quite intimidating. Concentrate on in terms of visually what's going on rather than so much getting wrapped up into some fairly intimidating math and perhaps some symbols that look like they're a little bit beyond the scope of this course. So let's take a look and try to understand what this concept of a wave function is. And when we think about a wave function, we oftentimes use the Greek letter psi, uppercase or lowercase psi, depending on the application, to express the wave function. What is the wave function? Well, it's really a mathematical description of the quantum state or the properties of the particle. And it's important to understand that oftentimes will simplify a system to only include one particle or maybe, a couple of particles. But when we talk about the wave function, in each situation, there's only one wave function, okay? It can be a combination of other wave functions from simplified systems, but we're dealing with a simple, or I should say it's a single wave function for any of the systems that we analyze. So again, psi, if you see different expressions for psi, sometimes they are intimidating. The value for psi or the function for psi is oftentimes complex. But again, understand what psi is. It is basically the mathematical description of the quantum state of the system. Usually, again, we analyze a single particle, and psi exists for all points in space and all times. So it is a function of both space and time. And when we go back to our little model of our particle, we oftentimes represent our particle as this wave packet. We can talk about psi in terms of what is the frequency or the frequencies of this packet. What is the position? Actually, psi can be used to find a number of different properties of this particle. So let's return to the double slit problem. Now, we can do this with a single photon. We can do this with a single electron. But when we think about this double slit problem, we know that by sending a single particle through the double slit, that's going to arrive on some screen. It's going to interact with the screen, giving up some of its energy. So what we first have to understand is that the wave function of this particle really exists in terms of all the space in between. So the wave function is basically restricted by these two openings. That produces an interference effect. And that, of course, is going to have a very important impact on the probability of where this single photon or single electron is going to land before it releases all of its energy, okay? Also, think about the wave function as it's passing through this double slit. We sometimes picture the interaction that it makes with a single point here as the collapse of the wave function, okay? Once it makes that interaction, the wave function is no longer located all through space. This particle, the photon or the electron, is given off its energy, and really this is the end of the problem. So we know from interference that when we look at the interference pattern due to the double slit, it's going to have sort of this cosine squared or sine squared like dependence, okay? And you get different peaks with where the maxima of constructive interference occurs. You get different valleys where the minima occurs, okay? So we see this type we can see this type of intensity distribution if we send many electrons through or we send many photons through, all right? The wave function at the location of the screen. Now we're going to just, take a look at a very simplified version of what's going on. And then look at the wave function at the screen. It is going to basically have peaks and valleys. And because the square of this function, okay, represents the intensity, the square of the wave function is going to represent the intensity that we see for many, many electrons or many, many photons, all right? A peak will indicate a more probable place that we get electrons or photons, and a valley will also indicate a more probable place. So here we can imagine that this particular wave function at the location of the screen for these electrons or for these photons would be some function AX, cosine AX, okay? So the intensity that results will be cosine squared AX. So here's one way of trying to, understand what this wave function represents. At least the square of the wave function represents the probability of where this particle is, or if it interacts with the screen, where this particle is going to interact. Now, if I want to calculate the probability that the electron or photon will end up in this purple box right here between position x1 and x2, the way that I would calculate this is the probability between x1 and x2 would be the integral from x1 to x2 of psi and psi star dx. Now, this is an important point here. When I'm doing this probability here, psi can be a complex function, okay? So if I take the complex conjugate of this, I would basically reverse any of the signs where an I was present, okay? So for instance, we know through Euler's equation that e to the I kx is actually cosine kx minus I sine kx, okay? There's a very strong association with complex exponentials, cosine, and sine, all right? So for instance, if let's say that psi was equal to, I'll use this little Gaussian here to keep it, keep the envelope, attenuated as we go in the negative and positive direction. But here we see this e to the I kx. We would then with psi squared multiply it by, change that sign to e to the minus I kx. So once again, taking the probability that the particle will be in any location, usually involves squaring the wave function, or more precisely, integrating the wave function and its complex conjugate over a particular distance where I want to measure the probability. Oh, just going back a point, the probability of the particle landing someplace, if I integrate this over all space from negative infinity to infinity, that probability has to be 1, because we have to accept the fact that the electron or photon is going to land someplace, okay? So if we allow it to land over all space, the probability that's going to land is going to be 1. So we can, obviously calculate the probability of where these particles are going to land. at a particular location. Of course, if we do this same problem over and over again, we will get an interference pattern of constructive and destructive interference for many particles, many photons, many electrons. We can also use this wave function to find out other properties for a particular particle. So for instance, if again the particle was described by this function psi, if I want to know where is the average most likely position that I would find this particle, then what I do is I actually use the position. I use x. Okay, this is technically a position operator, which means when I put it in this integral, and again, I'm trying to keep this as simple and conceptual as possible. But for instance, if I want to know where the average of the most likely position would be, I would put it between the wave function and its complex conjugate, and then integrate over all space, and that would give me the average value for x, or what we call the expectation value for the position. Now, again, psi represents the information of that particle, or it represents the information of that quantum state which the particle is in. So if I wanted to know other things about the particle, I could use other operators in this integral. Now, the problem is this integral is with respect to position. So the position operator is really quite simple. It's just x here. But if I wanted to use other properties, such as I wanted to calculate momentum or kinetic energy, we'll see that we need to use other forms in our equation. So again, here's our position operator. Here's our expectation of position. And again, our position operator in this case would be x. Sometimes this can be represented by this bracket notation. And again, the bracket notation has actually much more meaning than just this integral that we show above. But again, this can be a different way to represent the same idea, but in a more compact form. All right, and again, you'll actually see this in many other applications besides just finding the expectation position. It has a more general purpose than what I've represented here. So again, position, we say these quantum operators, which we can place inside these expressions. The operator for position is just x, but let's say that I wanted momentum. So then I would put in the momentum operator, which is actually a little bit more complicated than just inserting p in there, okay? And the reason for this is because I'm integrating with respect to position in that integral that I showed previously. If I wanted angular momentum, there is an operator for that. If I want kinetic energy, there's an operator for that. So the overall picture, which is I think more important here, is psi has the information about that quantum state. And we can use different techniques to get out things like, okay, where's the most probable position for that particle? Okay. We saw that earlier when we, did psi squared, or psi times psi star integrated. Where is the where's the average of the most likely position? Probably not saying that properly. What is the expectation value for the momentum? What is the most probable momentum? What is the most probable angular momentum? What is the most probable kinetic energy for that particle? All that information is locked inside this wave function. We can get that out. That's the power of using these operators and using this wave function. So again, here would be how I calculate my expectation value for momentum. And as we'll see with our next session, the Heisenberg uncertainty principle, you're probably a little bit confused as to, well, doesn't the particle have a position? Doesn't the particle have a momentum? Doesn't the particle have a kinetic energy? What is this expectation value? Okay, it sounds like it could be something else. Well, again, these represent the most probable value that I will get back in terms of momentum, in terms of position, okay, in terms of kinetic energy. All right, because in quantum mechanics, there's actually a spread, that there's an uncertainty in the different values that they can have. Okay. Now, one place you've seen a wave function represented, or at least the probability of a wave function represented, is in the hydrogen atom. If you've taken chemistry, you're well aware of the n equals 1, the s orbital, is often represented by a sphere. Here we've sort of represented it with different colors to represent different probabilities. For the s orbital, it's most probable at the center at the n equals 1. At the n equals 2, we have L equals 0 or L equals 1. And the L equals 1 state actually has 3 different possibilities for ML. And we can see here that the n equals 2, L equals 2 actually has a radial node here. So it's actually a sphere with a shell of probability around it where the electron would be if we're in that particular shape. Of course, the p orbitals have sort of a dumbbell shape to them. But again, although these are not really the wave functions, they're pretty close. They actually represent the probability, which is the wave function squared. So there would be one particular application for this. Now, the problems that we're going to go through with regard to quantum mechanics, and again, please concentrate on the conceptual problems. So we'll look at the uncertainty principle first of all. So again, we know that for this s orbital, the electron doesn't necessarily have a absolute position. It's not in this planetary orbit around the nucleus. It, in fact, is a standing wave. And the most probable place that I would find the electron, if I actually tried to measure it, would be, at the very center of this. Okay. So again, with these standing waves, the Heisenberg uncertainty principle does tell us that a wave does not have an exact position and doesn't and momentum, and that it's limited in terms of what the spread in positions can be for a given spread in momentum. All right, but we'll look at the hydrogen atoms, probably one of the more complicated systems to look at, but we'll look at a simple one-dimensional particle in a box, and we'll look at a harmonic oscillator. But again, these wave functions represent the information about the quantum state of those particles. And we're really treating these, the particle in the box, the harmonic oscillator, even the electron in the hydrogen atom, we're treating them like they're the only particle in the universe, and that this wave function is describing them. And that's an approximation for what we really see in nature. Okay.